So we are at the interface between, now we'll use the official terms, a p-doped and an n-doped semiconductor. Okay, and the main physical picture that you should all keep in your head is basically for distances larger than dc or smaller than dp. Basically, all the additional electrons that we had in the donor states moved to the conductance band. Why did they move to the conductance band and didn't stay at the lower energy of ED?
Entropy.
Entropy. And basically all the acceptor states in the acceptor band were filled up by electrons out of the valence band, leaving me holes in the valence band. And something else is happening in this region, the area around the interface between the two semiconductors or the two dopings. Here, basically, these guys do not move to the conduction band. They move to the acceptor states. Why? Because the difference in energy here is large. But at some point they can't continue this game because it costs too much electrostatic energy. That's the physics. Now we spent some time in expressing this physics by equations, by the Poisson equations, and we got the potential in this system. Basically, as a reference, let's start potential at minus infinity. We have some other potential at infinity. What happens up to here?
Nothing.
Nothing, because there's no charge. So nothing happens here, nothing happens here. And here we have a crossover between one to the other. That's the explicit form we have written down in the previous lecture. Okay, so far so good. So we have charge here and here, and that's the depletion range, which is usually of order of a few tens or hundreds or thousands of angstroms, depending on the material and the amount of doping, as we have written explicitly in the previous lecture. Okay. So we understand everything. Well, we understand almost everything. What are we missing here? What happens when we want to pass current through this structure? Okay, it's not a normal conductor. First of all, it's a semiconductor, basically similar to an insulator. Second, we have here some potential step in the middle of the system, which we don't have in a regular conductor. Okay, so how do I express the fact that I want to get current through the system? Any ideas? When you want to pass current through anything that you have.
Apply a field.
Do you apply a field?
Electric field, no? Let's go.
Let's talk about a DC device. That's all we do here. Do you apply a field? Well,
You want to pass current, you have a voltage.
right, you apply a voltage. Connected to a battery, right? That's what you usually do. Okay. What does applying a voltage do?
That's a field.
Right, but if I'm looking on this picture,
Move charges.
yeah, but moving charges would be complicated to show here, right?
Increases the energy.
Right, and how do I express it?
The bands will be higher.
I'm changing the potential. Particle going from here to here gains whatever the internal potential is, plus the external potential. That's all you did in high school. Was you got some circuit, they told you it's connected to a battery, the battery has a certain voltage, and the particles that went through it acquired this voltage unless there was some resistor in the way, right? That's all you do. So, when we started this game with no applied potential, well, I've already said that, no point in saying it again. The only thing I'll add now, this is the internal potential that comes out because of the band structure. Now I apply a voltage. Okay, now I have to see what flows here. What is the current here? Okay. Where will this additional voltage occur? Well, the voltage creates an electric field, right? Where will this electric field be expressed? Where will I be able to measure it if I could go into the sample and measure it?
On the borders,
Which borders?
like infinity and minus infinity.
Where will the change in the voltage occur?
The ions.
Well, a change in the voltage will occur mainly in the depletion range. Because there I have charge, it can do something. What will it actually do? Let's go back to what we have written in the previous lecture about the depletion length. Okay, and we wrote also for dp. Similar different arrangements of constants, but doesn't matter. Okay. Now, let's call it D0 with no external applied current and P0. Okay, now does something change here or here? Nope. Let's ignore this and Okay, here I didn't do anything but substitute delta phi 0 with delta phi. Now, assuming, well, let's leave it at the moment at this. Applying an external potential, what will it do? It will change the area of the depletion boundary, right? So I can rewrite not very surprising. What does the potential at the end of the day do? Change the distance here. So it can either increase or decrease the size of the depletion range. Okay, what does it do for the current? Okay. If I'm looking on what happens here for the holes, I can have here two things happening. One, charges from here coming and filling up these guys, right? So that's a, if I'm looking at what happens here, I'll have holes moving from here to here. Okay? And the second thing that can happen, I could have holes coming back from here and accumulating here. One of them is probable and one of them is improbable, right? One of them is going down the slope of the potential. The other one is going up the slope of the potential. So let's define. Which is also known as a generation current. So now you could wonder, why do we have all these cumbersome terms? Someone can guess? Ask again. Why do we have all these strange terms? Generation current. Why do we need this name? There's nothing special about it. Put yourself in the 50s and you are a physicist working in semiconductor physics, condensed matter physics, then it would have been called solid state physics. And you have an electronic device. To whom do you have to explain it?
And is used to current flowing from plus to minus.
You're almost true. You're explaining it to a bunch of electrical engineers that are used to work with tubes. So you have to take the terminology that they are acquainted with from their work with vacuum tubes and apply it to a new device that they understand nothing about. So you wouldn't explain them this whole band structure. You see, it took us a few lectures to get to the point where the concept of band structure, where are the donors, where are the acceptors, takes time. On the other hand, these guys are used to the terminology of vacuum tubes. They had these currents. Comes out from a different physical mechanism in tubes, but the idea is the same. You have one direction that you can flow current, the other direction you can't flow. So you use the terms they are well acquainted with. That's these terms. Therefore, you'll have terms that you can scratch your head and ask yourself, why did they complicate the language so much? Just say a current from N to P or for P of N, and that's that. Why give them name? The reason is you had to explain it to a community of electrical engineers that will use these devices. You don't invent a new terminology for people and then have to lecture them for 2 months what it means. No, you use the language and that's that. Okay, so don't remember even if I use this. This is the N-doped side. This is a P-doped, which is just. And this is in the language of electrical engineering. Someone knows? Yeah, but it has another name.
The device?
The structure. NP junction. NP junction or PN junction. What's a transistor?
It's two, like 3 junctions. Or 2.
2 junctions.
Two
But
junctions.
what is it called?
NPN or PNP.
NPN or PNP? Depending on how you built it. Okay, so we have our NP junction. So we have a current from N, a current of holes from N to P. Now you can stop me a moment and say, well, in one direction it makes totally sense, the other direction it doesn't make any sense. Right? Now remember that you have here, you are living at finite temperature. Finite temperature, you'll have both kinds of currents. One of them is just going down the slope, the other one is going up the slope. Going up the slope will have a smaller probability. Maybe, let's see, but both of them are probabilistic. That's thermodynamics. You have enough energy to climb a slope also. Okay, why am I saying this whole long discussion? Because at the end of the day, when I have V equal to 0, I have a steady state situation, and the population doesn't change with time, which means basically that if due to a thermodynamical fluctuation you have a hole here and it moved here, you have to have the same probability of moving from here to here. Okay, so let's now express as mathematical expressions all this chit-chat that I expressed here in words. So at V equals 0, it's a steady state. Now, can I say something about JH recombination? Recombination is, we'll check up what I have written, because even I don't remember what are the terms for each one of them. These are holes moving from here to here. Remember, potential for, and that's the reason why we are working with holes and not electrons. Actually, it doesn't matter, but since potential is for a positive test charge, makes life a bit easier to express everything for holes. Okay, so this guy has to move from here to here. Costs energy. What is the probability at finite temperatures that it will occur? Exactly what's written here. What else could it be? Okay. We were close. Okay, just taking this insight, expressing the v equal 0 result. What is the combined current for holes? Of course, when we have V equals 0, we express this to be 0. Whoever went from left to right will have the same number going from right to left. Okay, I could return on to the same story with electrons, just remembering to do a plus and minus conversion because they're negative here, and I'll get basically the same expression, so I can rewrite remembering to put the correct sign for electrons. I'll end up with it So what does this actually mean? First of all, let's check if we didn't miss anything. So I want to know what is the current as function of the voltage. Okay, what should be fulfilled in any condition?
Will you be in voltage difference?
Yeah, exactly. At V equals 0, I shouldn't have current. If I missed that, I got a perpetuum mobile. I could perhaps patent it, but it would be wrong. V equals 0, this is the equal 1. It's okay. Okay, to the left, I have a negative value. E to the power of a negative value is smaller than 1. So I'll have something that is equal at, let's say, V minus infinity to minus this one. But here basically I ramp up the voltage, I have stronger and stronger current that grows exponentially. So basically, this is the current profile of a diode. Why? In one direction, I can get through a small, for a good diode, insignificant current in one direction. Why will I always have some kind of current? Because it doesn't matter how much I increase this guy, I will still have fluctuations that are able to jump above them. In the other direction, the fact that I have reduced the height of the barrier causes me to be able to pass current exponentially more. Why? Because as in anything in quantum mechanics or in statistical mechanics, to jump above a barrier has an exponentially small probability, and I lower the barrier, I make the probability exponentially higher to go over it. So this is the world famous diode. Okay, this has been a very, very general calculation. If you think about it, we nearly didn't put any information beyond this thing and some consideration on what happens in equilibrium. Pulling out this connection, basically. Okay, we would like to say something also locally. Why? First of all, it will enable us to feel the physics better. Second of all, if we run into a more complicated situation, it will help us to express what's going on. So basically what we are going now to do is to write down the local behavior, meaning the x-dependent current and the x-dependent populations at any point. Of course, at the end of the day, we have to return to this behavior.
You do know that for low enough voltages, negative enough voltages, you can have a current, but then you destroy the diode.
Well, what happens if you put a strong enough back voltage, as it's called? You basically, if you have something above the gap, the whole picture breaks up, right? And you have also problems with heat generation that mess up your conductor. But that, in a sense, is an uninteresting effect because I can burn out any insulator by putting a high enough voltage, right?
Yes.
So this is an insulator with a particular behavior, and you burnt it out. Okay, but this part, the reproductive part of it, the thing that you can put a voltage in. At the end of the day, what is one of the main usages of a diode? Much before, before electronics, before actually, what did they mainly use the tubes for?
Switches?
Even before. straightening AC
Rectifying.
rectifying. That's why a diode is also known as a rectifier. Basically, you put in an AC component, so you'll get current going in one direction and the other. You put in a diode that will go in one direction, but almost not in the other direction. So it's straightening up an AC current. So in AC current, you're switching it, whatever, 200 hertz, 100 hertz, whatever your electric grid is. So you need it to be repetitive and well behaved. And that's exactly right. Okay, and that's one reason why I'm doing it. The second is basically the equations that I write down are relevant for any current carrying media and is used for modeling conductors, semiconductors, whatever. And it's a very nice connection between something you know, current in a medium, and some component of statistical physics that you've heard. I don't know how proficient you are in using it, diffusion. Okay, because until now, basically, we modeled these electrons as when we started with Drude. What was our assumption? You have a conductance, which is a material property. You put an electric field. You get a current, which is proportional to the conductance, some internal properties of the system, and times the electric field, right? We're missing something there, and it becomes important for situations like diodes, but also in general. Can I have a current without an electric field?
Yes.
When?
High temperatures?
For example, or if I inject a surplus of electrons in some region, right? If I put in somehow additional electrons, a surplus of electrons at a given area, what will happen? Well, push out. Now, classically, how will I describe this pushing out?
Brownian motion.
Brownian motion, diffusion. So current and diffusion have a connection. And the guy who knew how to connect all physics, Einstein, of course.
But it is a field. I have a field.
Came out with the theory of the fluctuation dissipation theory, connecting two apparently different fields of physics. Fluctuations, which is thermal fluctuations, and dissipation, which is electric current, which at first sight not connected at all. So that's the reason why the deeper reason why we are doing now this exercise for the behavior of the local current in these structures.
do have locally there an electric field.
Yes, but let's look how I'm treating it. Okay?
And we also saw in electromagnetic fields course you can calculate the field inside the specific regions in the material.
Of course. So we're doing a local calculation of the current. So, my basic building block are the local densities of electrons and holes. My second building block is, as you said, the electric field. So I have actually either the potential, it's best to look on it that we have the potential and the densities which express the properties at a given point. What did I write here? One term is just the influence of the electric field. In a moment we'll see what is this mu. It's known as mobility. Again, when we're talking, actually also with physicists, but with engineers even more, mobility is a property of the material. In a moment we'll see how it's connected to the conductivity or resistivity of the material. So this guy is the mobility. So that's one influence. But if I suddenly created some excess of electrons at a point, they'll diffuse from there. This is the second expression that we have here. And all of it is the current of the electrons at a given point. won't come as a great surprise that we have the same expression up to plus minus for the behavior of the holes. Someone can tell me why I have here a minus always? The fusion equation always comes with a minus.
You always go from higher to lower.
Exactly. On the other hand, the response to an electric field depends on the sign of the charge of the entity. Okay. First of and it's not necessarily the same because holes live in the valence band, electrons live in the conduction band, and it's not necessarily the same mobility. Okay, but mobility is a new animal. We haven't met it till here, of course. At least most of you have. Any electrical engineers here? You met mobility? Okay. Request a refund. Okay, so this is a form that we are familiar with. This is how I've written it up to the charge here. Okay. Obviously, they are just different names to the same quantity. So, sigma, you remember from the first lecture that we have discussed electrons or current or conductance in a sample? What is the simplest expression that we have for sigma? No, our first attempt to understand the Drude model. As bad as the physical description is, it's still something that we can use, and you'll see that in a lot of situations it's not so bad. So I'm just writing the expressions that we had. So what did the mobility give us in comparison to the conductance? We lost the density of electrons. So the mobility, in a sense, is, well, I can't say that it's a better description of the material, because in the description of a material you have also the density of electrons there, but it's the density, it's the conductance divided more or less by the density of electrons. So it's one conductance per electron. Not a good description, but this is it. So we know our components here. Okay. If we were in if we were at equilibrium, what would be the behavior of N or P in a semiconductor? Well, at the end of the day, these guys, you remember we wrote it several times. We had Nx So if I remove this part, the good old description that we have given 2 or 3 lectures ago, the only thing I'm adding here is phi. This is the behavior under equilibrium conditions. What happens at equilibrium? So what happens to the current? Is current at equilibrium, meaning with no applied external voltage. 0. Should have jumped immediately. Equilibrium, no current. Why? Because if you had current, you would have put the electrical company out of business. So, but I know also Nx for equilibrium. give it here. So I can go in, perform the derivative, and see what do I get. Okay. What is E? Minus the phi to the x, right? It's known as the Einstein relation. People, for some reason, when you say Einstein, relativity, quantum mechanics, a good old thermodynamic solid-state physics relation that he was the first to express. Now, in some sense, this is an amazing relation. Why? Left hand is something that comes out of electromagnetism, out of Maxwell's equation. Response to an electric field. Well, it's not really, you don't need the whole glory of Maxwell equations. Coulomb is quite enough here, but it's something that comes from that side of physics. If you look on this guy, D, K, B, T are all thermodynamical relations. This is sometimes also known as fluctuation-dissipation relation. Thermodynamics deals with fluctuations, local change because of the fact that you're coupled to a bath, which is the temperature. Here, you have something that comes out of classical current, classical electromagnetism. And what is the connection between those two guys physically? Put your hand on a resistor. It's hot. Fluctuations and dissipation both have something to do with heat. And here we wrote down this connection. So, okay, what are these?
Continuous line equation.
The continuation equation. Right? Okay, what is everything actually here?
Generation and generation.
Exactly. These are under the assumption that I have a charge, and the only way that it can disappear is by moving out. Or the only way that it can be created is by moving in. That is great if I have a charge or a particle that can't be created or annihilated. For our game,
Can.
it can. I can have a fluctuation here, thermal fluctuation, where a hole or a charge will be created. Of course, not created, you'll have a pair there, but could be, so I have to take this into account. So I'll rewrite these equations by adding a term. Take it in a different color. Okay, what does it tell us? It tells us something about the fact that my population can change with time, not connected to current. It doesn't move from a place to place, but is created. What is the simplest model that we can put regarding creation or destruction of excess of particles or holes? Okay, first of all, could there be continuous creation at a point no matter how many particles there are there? No, I want to limit it somehow, right? Here we are giving a phenomenological description, so we're stopping and thinking about the simplest models that we can do here. So, if I'm at equilibrium, I have a given average number of particles. So if I'm going much above it, I have to have a mechanism that will lower it. If I'm going much below it, I have to have something that will fill up. Okay, so the simplest picture for such behavior Why is this? First of all, it's simple. It's linear, right? Okay. Second of all, I have here a dependence on the average number of particles or holes. That's a minus n0. So if I'm above it, this term is negative and it goes down. If it's below it, it's positive and it goes up. So it gives me the right direction. It's simple, i.e. linear. And all the physics, properties of the system and so on, I'm pushing into a time constant which tells me how fast does that axis go back to normal, or how or vice versa. If I have a smaller number of particles there, how quickly does it go back? The rate at which these fluctuations disappear. Okay, we already forgot at this point, but we are assuming equilibrium. So we can rewrite these equations. So what do I mean by equilibrium? These guys are equal 0. I'm far enough from the depletion region. What happens far enough from the depletion region? What was the special behavior at the depletion region? I had charge there, right?
Far enough away there won't be any imbalance.
No imbalance and no electric field.
Alright.
So if we go back So what did I do here? I moved to the edge. It's a place at infinity where I know the number of holes. and looked at the profile of the number of holes anywhere else in the system at the point of x0. So if I had some local perturbation in px, it will fall off exponentially from this point. And this enables me to define the generation current So, what was the purpose of this whole exercise? We defined the generation current. What is the probability of seeing current that comes out of the fluctuations in the system? So, we did it in a classical manner, just out of the fluctuation dissipation theory. What is important in this whole exercise? Not so much the behavior of semiconductors, it's important, but for you as physicists, the dissipation, fluctuation, or Einstein relations is very, very fundamental, appears in every field of physics. Why? Because it connects you thermal fluctuations, things that you have no control as a result of temperature fluctuations, a completely random process, with a process that is associated with applying a field. In this case, the electric field, but you have also this fluctuation dissipation when you apply a magnetic field in the susceptibility of a magnetic susceptibility of a system and in other connections. And this is an important connection that it's important to remember here. The details of getting this relation is relevant to people who are doing semiconductors, not so much for anything else, but the main idea is an important idea. Okay, so the next thing that we should say a few words is about the transistor. The idea there is, I'll do it actually in 2 minutes. Okay, so I'm putting a diode, let's say a PNP junction. Okay, let's take this picture and connected it back to back. What is special about a transistor? What is the basic difference between a diode and a transistor? Which you can explain to a 3-year-old. Someone who mastered counting. A diode has 2 connections. A transistor has 3. Why? Because you have a connection here and here, and a gate. Now, the important thing to remember at a cartoon level description of a transistor is you control the current from here to here by the gate. You open and close it. Right? Now, a transistor has the same behavior if you're trying to move current from here to here or from here to here. Why? You can see it immediately. What stops the current moving is the steep slope here or here. What does the gate do?
Lowers the slope.
Lowers or enhances the slope. So once it's lowered, current flows easily. Once it's higher, you have only some remnant of current going through due to the fluctuations. Well, you don't want them too large because then it's not a good switch, but if it's quite small, this is the whole idea behind a transistor. Something that controls the current from two legs by the voltage on the third leg. And that's a transistor. From there on, all the complicated behaviors are built out of these components. Okay, where will we continue from here? The next two lectures I'll bring some more modern applications of condensed matter. One of them will be persistent current. There's interesting connections to things like basic quantum mechanics and the Aharonov-Bohm effect. This, I don't know, it's self-defeating, then I'll talk to myself. Won't be in the exam, but people who will be in the class and perform a small homework will get additional points for the course. Okay, let's see if it will bring more than one person to the lecture, but it's also an interesting basic, well, Aharonov-Bohm will be the first, the second I didn't yet decide what I'll do. Things that anyone who wants to continue in physics, it's fun and important to hear about. Okay.
Thank you.
Thank you.
Thank you.